So in this video, we're going to use the difference quotient to find the instantaneous speed of a falling object. The problem we're going to be working with is this one. Suppose that the height of a falling object, t seconds, after being dropped from a height of 64 feet is given by height as a function of time equals 64 minus 16t squared feet. And it says find the instantaneous speed or speed. If you don't say average speed, then you assume that it's talking about instantaneous speed. We want to find the speed at which the object is falling 1 second after it's been dropped. So I'm going to pull open GeoGebra Classic here, and I've gone ahead and graphed the height model. So the height model, remember, was given by, let's hope things work. The height model was given by height as a function of time equals 64 minus 16t squared. So I have the vertical axis is my height axis in feet, and my horizontal axis is my time axis in seconds. And if I want to know, well, one thing I want to recognize is that even though when I graph 64 minus t squared, I get this full parabola, the entire parabola doesn't make sense. There's a contextual domain for this problem that starts when time is equal to 1 and time is equal to, between time equal 1 and time equal 2 is when the ball's actually in the air. So at time equals 0, the ball starts up here at 64 feet. And 2 seconds later, it's on the ground. So my contextual domain is time is an element of the time interval from 0 to 2. So only the part of the height model in quadrant 1 makes any sense in the context of a dropped object. And the problem's asking me to find the speed of the ball 1 second into the flight. So the object, at 1 second into its flight, at the 1 second mark, when I plug 1 into the function here, I get 64 minus 16 times 1 squared is 48. So the ball's 48 feet, or the object is 48 feet above the ground. And I want to know the speed of the object at that time. And one thing that we could do to estimate speed is we could drop another point on the graph, and then we could put the secant line between those 2 points. And we know that the slope of the secant line, which is going to be a delta height over delta time, right? Change in height over change in time is your delta y over delta x. It's going to be the slope of the secant line would give us feet over seconds, or feet per second. So just like in the previous homework, we saw that the slope of a secant line gives us an average speed. So for example, I could calculate the slope of this secant line over the time interval from 1 to 1.55, and that the slope of the line then would give me the average speed over that time increment. And I could use that average speed to estimate the speed at the 1 second mark. And the big idea is that if we let this point 1.55 become closer to the point at which we're actually interested in the speed, in other words, we let the time difference between them become smaller, then the slope of the secant line, or the average speed, would give us a better and better estimate for the speed when t equals 1. So we want to let the delta t go to 0. And if we let it go to 0, we just have a tangent line sitting there. So the big idea is that the slope of the tangent line to the graph, will give us the instantaneous speed when t equals 1. So just like the secant line gives an average rate of change or average speed, the tangent line gives an instantaneous speed at a particular time. So what we're going to need to do is actually calculate the derivative of the height model, because the derivative of the height model is the function that will tell us the slope of the tangent line. So I need to calculate h prime of t, and to do that we're going to use the difference quotient. And remember, the difference quotient said, hey, to get the slope of the tangent line, take the limit as h goes to 0 of f of x plus h minus f of x, and divide it by h. And because my function's name is h, I'm going to want to use a letter other than h to represent the time difference, which is what h represents. H is going to equal the difference between t sub 2 and t sub 1. So I'm going to change this a little bit. I'm going to, instead of using h, I'm going to use a to represent the change in time. And I want to recognize that instead of f, my function's name is h, and instead of x, my variable name is a t. So I'm going to go ahead and set up the difference quotient for this height model. So it's going to be 64 minus, sorry, I need to take the limit as a goes to 0. I'm using a instead of 8. So I'm going to take the limit as a goes to 0 of the difference quotient. So it's going to be height as a function of t plus a minus the height function itself all over a. So everywhere I see a t in my height model, I replace it with t plus a. So I'm going to take the limit as a goes to 0 of 64 minus 16 times t plus a squared minus the original function, which is just 64 minus 16t squared. So 64 minus 16t squared. And this is all over, instead of h, we're going to put all over a. And again, the only reason for doing this is we don't want to mix up the number we're using here to represent the change in time with the name of the function itself. And then I can start to simplify. So this is going to run out just like it has in the previous video. Start to simplify. Take the limit as a goes to 0. We can start working on the numerator. 64 minus 16 times t plus a squared is going to be t plus a times t plus a. And if we multiply that out, we get t squared plus the middle term twice, so 2 at's, plus we'll get an a squared, minus, distribute this minus into parentheses, minus 64, minus plus 16t squared, and it's still all over a. See if anything will simplify. We get 64 minus 64 is 0, so we can get rid of that now. So moving down a line, the limit as a goes to 0. Distribute the minus 16 into the parentheses right here. So I'm going to get minus 16t squared. Minus 16 times 2 is minus 32at. Minus 16 times plus a squared is minus 16a squared plus 16t squared all over a equals the limit as a goes to 0. Simplify things if we can. Let's see. Negative 16t squared plus 16t squared is 0. So that's going to leave us with minus 32a times t minus 16a squared all over a. And I see an a shows up in both terms. I can factor that off. Equals, I'm going to get rid of, no, not yet. I am going to turn my tangent line off and get it out of my way. There we go. Except I need to get my pin back. So the limit as a goes to 0, the a shows up in both terms in the numerator, so factor it out. A times minus 32t minus 16a all over a. And a divided by a equals 1 as long as a does not equal 0, which it won't. We're letting a approach but not get to 0. Equals the limit as a goes to 0 of what's left, negative 32t minus 16 times a. And then I want to recognize right here, I just have a linear function. So it's defined from negative infinity to infinity, which means from a previous theorem, we can just plug the 0 in now. So equals, I'm going to drop the limit notation, negative 32t minus 16 times 0 equals negative 32t. So h prime of t is negative 32t. So my derivative of my height function, my derivative is just h prime of t equals negative 32t. And the ball is in the air between 0 seconds and 2 seconds. So the ball, or whatever object's been dropped, is in the air. Time is an element of the interval from 0 seconds when it was dropped until 2 seconds when it was on the ground. So if I plug in any time in this time interval during which the object is in the air, h prime of t will give me the speed, or the instantaneous rate of change, or the instantaneous speed of that object at that time. So if I want to know how fast the ball is falling 1 second into its flight when it's 48 feet above the ground, I just plug time equal to 1 into my derivative. H prime of 1 equals negative 32 times 1 equals negative 32. And this is going to be feet per second. So that's going to be my speed. The speed when time is equal to 1 is negative 32 feet per second. And the feet per second, where we're getting that from, is when you calculate the slope of a line on this graph, you have a delta h over delta t. Remember, delta h is height in feet, and delta t is time in seconds. So we're getting a feet per second calculation when we calculate the derivative. The slope of the lines have units feet over seconds.